Alright, so to continue from our lecture today, just a brief recap of the concepts needed before we move on to all of the active filters that we were supposed to cover. The concepts I want to go over again are just the basic impedances for AC analysis, as well as the basic inverting amplifier architecture. In this case, when we look at our impedances, resistance doesn't change. So a resistor in AC and an AC analysis is just a resistor. Capacitors, on the other hand, we represent as 1 over j omega c. And what's interesting is from this observation, if you look at omega, which is just 2 pi f, 2 pi the frequency of your input, what ends up happening is you can see that as the frequency increases, the impedance of the capacitor goes down. Another way that you can think of this is as frequency goes up, it's much easier for a signal to pass through a capacitor. On the contrary, an inductor's impedance is j omega L, and if you start increasing the frequency, you can see that a signal would have a tougher and tougher time to go through this impedance. The other theory that you need is the op-amp theory. So just a brief recap of op-amps. An op-amp has two terminals. It's a 3-terminal device that has 2 input terminals and an output terminal. The 2 input terminals are normally denoted as V- and V+. And the 2 rules which really govern the operation of an ideal and perfect operational amplifier is that V+ has to be equal to V-. And one of the reasons that happens is because the second rule, which says that there is no input current to the op-amp. So these I- and I+, or I have it here denoted as I1, should equal 0. Now, of course, in the real world this isn't true, but for our analysis, just to get the point across, let's believe that we live in that perfect world where we can say that. And then one of the common architectures I brought up in class and derived the transfer function for, again for you guys, was the inverting amplifier. So through basic node analysis and using the rules laid out here, we figured out that the gain of this amplifier is equal to negative R2 over R1, or it's the negative of the feedback resistance over the series resistance. So how can we use this to actually make active filters? Well, if you recall back from today, we covered RC filter networks. So you may think, okay, let's just throw some capacitors into our op-amps and congratulations, we have a filter. It's not that easy, and you're going to see very quickly why. So let's say that we try to make a low-pass filter. We say, okay, we remember that there was a resistor for a low-pass filter, and, let's make it an inverting amplifier so we already know the gain. And we're going to put the capacitor in the feedback. So we're going to call this V in, V out. This is just R. And for right now, I'm going to call it C. I haven't put the impedance in yet. So one of the reasons I really, really strongly suggest you get very familiar with the inverting amplifier is because once we can represent this capacitor and this resistor both as impedances, we can now treat them in the same way that we did the resistors in our inverting amplifier. So if we can get to such a way that we can get these resistance relationships, our gain is going to very easily just be the -1 times the feedback impedance all over the series impedance or the input impedance. So for our circuit here, it's pretty simple. So if we convert it over to impedances, I'm going to denote that with a green marker. We have our same input output. It's going to look the same, except for now we're going to call this Z1 and we're going to call this Z2. And I put them on the bottom so that I can write on top what their impedances are. So as mentioned earlier, up in the top of this, we said that, okay, resistors stay the same. They're just R's. Now, the capacitor, though, is different. It changes to 1 over j omega c. So in this case, these are both impedances. Again, they're treated just like resistors. So we know that the gain of our system, V out over V in, is going to be equal to minus the feedback resistance, or the feedback impedance, Z2 over Z1. Or in our case, we have 1 over j omega c over r, which through some math we can end up with a negative 1 over r j omega c. You may be, kind of confused. Well, what does this negative really have to do with anything? Well, first off, normally in gain, these gain equations, we look at the magnitude. But another way that we can kind of move that negative out of the way if it's really, causing you some issues is if we multiply the top and bottom of this equation by j. So what this effectively does is remove the j out of the denominator, but when you have j squared, you're going to get a negative 1. So through that multiplication, we end up with j over r omega c. So this is a point where some people got confused in the class, because we figured out that this should have infinite gain at DC. And rightfully so that people got confused, because we were talking about this concept that the low-pass filter should have, almost no, for RC it shouldn't have any gain. It should just have a gain of 1 in the lower frequency, and then the upper frequencies should dip down to negatives, so it should start attenuating. The issue was, as soon as you see that omega is equal to 0, or let it tend to 0, our gain explodes. So our frequency response plot, or Bode plot, if we have frequency on the x-axis, and we have gain on the y-axis in decibels, in this case, we'd start out all the way up at infinity. I mean, I can't draw all the way up to infinity on this thing, but it would start out extremely high, and you'd really be limited by the characteristics of the op-amp and all the parts you're using, but that's for a later lecture. So ideally, you would have an infinite gain, and you may look at this and say, okay, well, it looks like it's a linear relationship. I mean, if I increase omega more and more, my terms should start getting smaller and smaller. There's no squared terms or anything like that. So our gain will look something like this. And on the web page that I provided you in the sample circuits in every circuit, you can see this happen. And you might say, oh, well, at the really low bands or the really high bands, it curves off. That's because this simulation takes into the fact that these op-amps are perfect. So, is this something that we really want in our circuits for filtering? I personally say no, and the major reason why is because if we cared about frequencies from, let's say, 1 hertz to a kilohertz, and let's say we have 1 hertz here and 1 kilohertz here on our frequency plot, what's going to end up happening is my 1 hertz signal is going to have some ungodly amount of gain when it goes through this system, but our 1 kilohertz signal isn't going to be as amplified. So you don't have a linear passband, meaning that you don't have a really nice flat range of gains for the frequencies that you care about. And this is kind of a pain to design around. So what we can do is we can try to limit the effect of this low frequency gain spike. And you may be thinking, well, how in the heck can we even do that? You have to look and see that the troubling term is this denominator. So it goes to 0. How can we get it to not go to 0? To be able to do that, we add another component into the feedback. And it also allows you to have a lot more cooler designs for your circuits. So let me show you what I mean. So we're going to have the same R1, our input resistor. I'm going to put it into our op-amp, tie the positive rail to ground, same as before. I'm going to have our feedback capacitor. However, instead of just the feedback capacitor, I'm also going to add a resistor in parallel, R2 and C. Now this may seem very, very strange. You may think, why would I want this R2 here? But this R2 solves our problem of having the infinite gain at low frequencies. So what this means is, let's now actually try to find the transfer function. And I mean, I hate to sound, like the videos that you've had in high school and middle school, but I mean, I really would recommend pausing it now and trying to figure out what the transfer function of this system is before we move on. But if you don't have that patience, so here's what it is. You're going to end up with, my first step that I would do is, yes, you could sit here and do node analysis, but you're engineers. You should try and figure out ways to do to simplify your problems. And the first way that we can simplify it is if I can treat C and R as impedances, or again, like resistances, I know that I can combine parallel impedances. So in this case, if I call this Z2 and I call this R1 my Z1, well, now we have something that looks very, very, very familiar to us. And it looks like our basic inverting amp. And in this case, if we have V in and V out, we know that the gain is going to be equal to negative Z2 over Z1. Pretty simple. So in our case, what is Z2? So Z2 is going to be equal to the impedance of R2 in parallel with the impedance of our capacitor. And we know this is going to be R in parallel with 1 over J omega C. So if you remember your parallel, how to do parallel resistors, it's going to be equal to R times 1 over J omega C all over R plus 1 over J omega C. One of the things that I normally like to do is when I see a fraction in the denominator, it kind of bugs me. So one of the things that I immediately do is go, okay, I need to get rid of that fraction. So we do that by multiplying the top and bottom by J omega C. So again, multiplying by a form of 1. This is a great math technique that you really should become comfortable with. So our J omega C's on the top and bottom will cancel out. However, we still have to multiply R by J omega C. So our end result is going to be R all over R J omega C plus 1. Now, this R in this case is going to be R2. I forgot to write this down. So it's R2. Again, it's our feedback resistance network. This should look very familiar. So this term we had before. This R J omega C term. This is what kind of threw us off before. But when we actually put this together into the full gain equation, you're going to see that when we lower our frequency down to almost nothing, that we're actually not going to have infinite gain. So what I mean is we just calculated Z2. We know that Z1 is just going to be equal to R1. So our gain is going to be equal to minus, and I'm going to apologize right now for how painful this math is going to look, but it's really not that bad, over R1. So we can rewrite this as negative R2 over R1 times R2 J omega C plus 1. So this is the overall gain of this op-amp configuration. So if we were to look at the frequency characteristics again, so again, frequency on the x-axis and our gain on the y in decibels, what ends up happening is, now look what happens in this term when omega goes to 0. Our bottom term, our denominator, doesn't explode anymore. Sure, we lose the R2 term, but what we end up with at low frequencies, so at low frequency, so almost 0 or DC, so like DC, you end up with G is equal to negative R2. Again, the negatives, we're taking the absolute value here of the magnitude, so the negative is not going to be that much of an issue, over 0 plus, if you multiply this R1 in, R1. So we get R2 over R1. Now our gain doesn't go to infinity. Instead, it starts out here. And this set point is given by the ratio of the resistors. And you as an engineer get to pick this resistance. It also plays around with the, the frequency characteristics. But as mentioned before, these filters go up to a certain cutoff frequency. And the easy way to represent this is we normally have a point where it starts rolling off at 20 dB per decade. So this would still be considered your cutoff frequency, where the knee happens. As I mentioned in class, there's a special term for this, the 3 dB point. So now you've seen a low pass active filter. And in this case, look what happens. We have a much more linear passband, a much more flat passband, which is a lot easier to design around. You don't have to worry about, well, if my signal swings from 10 hertz to 100 hertz, now I have to worry about it being attenuated or have a different gain applied to it. So now that we've looked at the low pass filter, now let's look at the high pass filter. So to be able to talk about the high pass filter, I want you to take another, just a brief recap of why our initial amplifier architecture exploded at DC. It was because as the frequency was dipped down to almost zero or very low, it was extremely hard for the signal to flow through the feedback path, which meant that the impedance of the feedback, or Z2, started growing. For a low-pass filter, that's great. For a high-pass filter, we want the opposite behavior. We want, as the frequency increases, we get more gain, and low frequencies get attenuated. So hopefully in your mind you're thinking, well, can't we just flip the position of R and C? And you're right. So to go through the same sort of, to show you the flaw of just a basic implementation like this, we're going to show you, or we're going to go through the basic architecture with one capacitor and one resistor. We're going to put this into our impedance form, and in this case we're going to have our VN, Z1, Z2, and V out. So what's interesting is we already know what the gain's going to be. Gain's going to be equal to negative Z2 over Z1. We already know this. And hopefully by now you should be familiar enough with the impedances, and have heard me drone on about them long enough, that we know that Z2 is going to be equal to R, and we know that Z1 is going to be 1 over J omega C. So our gain is going to be equal to R over 1 over J omega C. And using basic, looking at this fraction, we can flip the denominator up into the top, and we can say that the gain is equal to RJ omega C. Cool. This gives us our behavior that we want. So you look right away and you say, well, at the low frequency end of things, when you look at the low frequencies, well, low frequency, omega is equal to 0 or close to 0. It's going to be really small, or basically 0. So we have a gain that actually is 0, which unfortunately for us, anybody know what the log of 0 is? Yeah, it's not good. So in this case, we're going to start off at the bottom here, and now we're going to just skyrocket off into infinity. So as frequency increases, we get more and more gain. This is, again, problematic, especially when designing circuits. So from a mechanical engineering standpoint, if anything's near a motor, you're going to have a lot of high frequency noise. And what this circuit does is, you may be, great, I'm knocking out all the low frequency noise I don't care about. But let's say that you have a noise spike. So you may be, dealing with a circuit where here's your voltage, or here's time and here's voltage, and you may be trying to read some DC level, but your DC level has all this little high frequency little jitter on it. The issue is, when it goes through the circuit, that high frequency jitter is high frequency, which means that it's going to be have its amplitude magnified by quite a lot. So again, we have this undesirable characteristic of our infinite gain and infinite problems. What we do instead is we take the same approach. We say, you know what? We want Z1 in our case. What's causing the problem here is that Z1 goes off and blows up. So we need to figure out, how can we fix that? How can we make it so that Z1 doesn't go to 0 as the gain goes high? We want it to go to some set point. So what ends up happening is we now can design a high-pass filter. Vn. So I'm still going to have our capacitor, but I'm going to put a series resistor with it. Same feedback resistor, same connections. V out, Vn, C, R1, R2. Okay? So in the same process as you saw before, what we're going to do is we're going to say, you know what, I can combine these into one impedance, and I can take this, take it as another, and all of a sudden it's like, well, that's easy. We know that gain is equal to Z2 over Z1 based on the inverting op amp, and in this case, Z2 is going to be equal to R2. That's pretty easy. Z1 is just going to be R1 plus the impedance of the capacitor, which is going to be equal to R1 plus 1 over j omega c. And from our previous, all of our previous examples and what I mentioned before with the inverting op amp, Z2 over Z1, which is just going to be equal to R2, negative R2 over R1 plus 1 over j omega c. So what's going to end up happening is, let's look at our frequency again. So frequency response, you're going to get tired of me saying, frequency response and Bode plot, but that's the name of the game here. So we started a low, very, very extremely low frequency. What ends up happening is we have R2 over R1 plus 1 over j omega c. As this goes to 0, this whole term goes to infinity, we still have 0 gain. And the way that we can represent that is we just have a line starting from down here and coming up to a certain point. So again, I mentioned, look at what happens as we start increasing the omega more and more and more and more and more. So what ends up happening is this term here, as omega goes towards infinity, this whole term goes to 0. You end up with 1 over something growing extremely large. It's going to be equal to 0. It's basically going to disappear. So in the case where omega is equal to, or omega tends to infinity, G ends up going to minus R2 all over R1 plus something that goes to 0, which is equal to minus R2 over R1. We now have a threshold or a limit that our gain can only go up to. And again, it's set by this R2 over R1 ratio. So our response will come up to here, come up to a point, and then flatten out. Again, this is an oversimplified version of our frequency response that we normally look at. So, and again, now we end up with this flat passband, which is something we can actually work with. The last filter that we need to look at is the bandpass filter. Now, technically, there's 2 ways that you could go about this, and you may be thinking, well, maybe I can just pass my signal through a high-pass filter and then a low-pass filter. So let me start out by showing you what a bandpass filter's frequency response should roughly look like. So, of course, we can only, we always have these, off to infinity type of moments here. So I'm going to end up with F in hertz, magnitude and gain dB. So what ends up happening is a bandpass filter filters out all frequencies except for a specific range. And you noticed this in the last lab when you measured what were the cutoff frequencies at the low end and the high end of your BJT amplifier. So what's going to end up happening is our passband filter should look something like this. There's going to be a point which is our FCL. So our cutoff low frequency point, our low frequency cutoff point, where it's going to go off into negative infinity up until this point. Then it's going to flatten out and be nice and flat and linear like we wanted. Then after a certain point, we're going to have our FCH. So we have our FCL, which is our low frequency, and FCH, which is our high frequency cutoff. And then it's going to start rolling off again towards negative infinity or 0 gain to fully attenuated. So the question is, what can we do to actually create something that has this frequency response? And hopefully you can kind of look at this and be like, well, it's sort of a combination between a high-pass filter. So this looks like a high-pass filter. And this looks like the behavior of a low-pass filter. So you might think, maybe I can just put one, or take the output of one of these filters and put it into another. So it would look something like this. And remember, we want to use our limited versions because we don't want things like noise to get extremely amplified, or all these DC terms to basically wash out any signal that we want. So let's have our input signal V in. Let's just say R1C, R2 into a low pass filter, and this will work. Albeit it looks a little sloppy, but this works. However, I will like to say, here's V out. This will work, however, it's not the most efficient method of doing it. It requires 2 op amps, double the parts, double the cost, all this type of stuff. So instead, what if I told you that we could do this all on 1 op amp? You may be thinking, oh, he's gone crazy. But really what it is, it's just a combination of the 2 of them on top of each other. Meaning that we're going to take our high pass filter, and instead of trying to make a second op amp, or use a second op amp, why don't we, in the feedback, just put our low pass filter components. Now we have something, when combined, by the powers combined, we end up with an R1, C1, R2, C2, V in, V out. So you may be thinking, oh, do I really have to analyze this? Again, I've been showing you tools this whole time how to treat these series and parallel impedances. We say, okay, we have Z1 and we have a Z2. So here's Z2, here's Z1. So if we can get it into this form of Z2 and Z1, we now know that the gain is going to be equal to negative Z2 over Z1. So Z2 is going to be equal to R2 in parallel with C2, which we know from our previous calculations is going to be R2 over J omega C2 all over R2 plus J omega C2. Z1 is going to be equal to R1 plus 1 over J omega C1. So I'm going to simplify Z2 a little bit, make Z2 equal to, I am so sorry, 1 over J omega C2. I'm going to multiply the top and bottom of J omega C2. Now we end up with R2 over R2 J omega C2 plus 1. And again, this all looks painfully hard in terms of math, but really it's all just numbers. So now we have G is going to be equal to minus quantity R2 over R2 J omega C2 plus 1 all over top of R1 plus J omega C1. 1 over J omega C1. Again, sorry for the math mix-ups here. Let me make this look a little bit better. 1 over J omega C1. Is there an R there? No. Alright, so is there math that we could do to make this simpler? Sure.
One eternity later.
R2 J omega C1. This just makes it look like way more of a hot mess, doesn't it? I'd really like this thing to stop adjusting on me. R1. Yeah. Okay. Not going to make it any simpler. With this pain of a gain equation, what we can see though is if we set our omega to 0 or tend it towards 0 or very low frequencies, we end up seeing that our gain equation turns into G is equal to R2 all over. This will become 0 plus 1 all over R1 plus we have 1 over J omega C. Omega goes to 0. This entire term goes to infinity. Now that we have an infinity on the denominator, this whole thing goes to 0. Cool. Now as omega grows in size, we put it to infinity. Our gain is going to be R2 all over, I'm just going to write infinity, all over R1 plus 0. So now we have infinity, we have something that is divided by infinity again. Guess what? 0. We can see if we use a software like MATLAB or if we use a simulation tool that our frequency versus gain plot, I'm really getting sloppy here, our frequency versus gain plot ends up looking sort of like what we predicted. Now, how high does the gain go? At what point are these low and high cutoff frequencies? That's for you to use the simulation tools that I provided you in the simulations to figure out exactly what impacts what. So really play around with that bandpass circuit and see what actually impacts the overall gain, what impacts how wide this band is, and this week in lab we're actually going to be seeing the impacts of all of these, and we're going to be building and designing one of these bandpass filters.